I welcome you all in my YouTube video channel. Today I will deliver lecture on Lattice Theory, lecture number 6, Part 1, in which I will discuss about some problems based on basic properties of lattice. Now we solve problem 1. Problem 1 is let L with partial order relation be a lattice in which this symbol and this symbol denote the operation of meet and join. This is meet and this is join. Then for any A, B belongs to L, so that number 1, A is related to B. For simplification, we say that this relation as less than equal to, but it is not actually less than equal to. It is a partial order relation of a lattice. So here we usually say A less than equal to B, means A is related to B. Here A less than equal to B implies that A meet B equal to A, and number 2, A less than equal to B implies that A join B equal to B. Firstly, we prove number 1. Since A less than equal to B, a given and also A less than equal to A for reflexive property. Therefore, A less than equal to B and A less than equal to A means A is a lower bound. Therefore, A is a lower bound of the set containing elements A and B. Since lower bound is less than equal to greatest lower bound, implies that A is lower bound and greatest lower bound of A and B is A meet B. This is number 1. Again, A meet B is greatest lower bound of the set containing elements A and B. Since greatest lower bound is a lower bound, therefore A meet B is a lower bound of the set containing elements A and B. Lower bound means this is A meet B less than equal to A and A meet B less than equal to B. Implies that A meet B less than equal to A. This is number 2. From 1 and 2, we get A meet B equal to A for antisymmetric property. Since this less than equal to A meet B and A meet B less than equal to A, so this is for by antisymmetric. Since here this A less than equal to B implies that A meet B equal to A. Now, if sign is both side implication, then we shall prove A less than equal to B by assuming A meet B equal to A. Conversely, let A meet B equal to A. Since A meet B equal to greatest lower bound of the set containing elements A and B, and greatest lower bound is a lower bound. Therefore, A meet B is a lower bound of set containing elements A and B. Therefore, A meet B less than equal to A and A meet B less than equal to B. Let this is number 3 and this is number 4. Since A meet B equal to A, therefore from 4 A meet B equal less than equal to B implies that A meet B equal to A, therefore A less than equal to B. By assumption. And proved. Now we shall prove number 2. Given that A less than equal to B, and since B less than equal to B implies that B is an upper bound of the set containing elements A and B. B is an upper bound. We know that least upper bound of A and B, least upper bound of set containing elements A and B equal to A join B. Since least upper bound is less than equal to upper bound, therefore A join B, this is least upper bound, and B is upper bound. This is number 1 of problem 2. Again, since A join B is least upper bound of the set containing elements A and B, and least upper bound is an upper bound, therefore A join B is an upper bound of the set containing elements A and B. Therefore, A less than equal to A join B and B less than equal to A join B. This is number 2, this is number 3. From 1 and 3, we get A join B equal to B by antisymmetric. Property. This is proved. Here, if this is both side implication, then we prove the conversely. Let A join B equal to B. Since A join B is least upper bound of set containing elements A and B, a least upper bound is an upper bound. Therefore, A less than equal to A join B and B less than equal to A join B. Let this is number 4 and this is 5, this is 6. From 5, A less than equal to A join B using 4, and proved. Now we solve the problem 2. In problem 2 we have two problems. Number 1, A less than equal to B implies that A join C less than equal to B join C. Number 2 is A less than equal to B implies that A meets C less than equal to B meets C. First solve number 1. Let A less than equal to B implies that A less than equal to B join C with basic property. This is number 1. Again, since C less than equal to C implies that C less than equal to B join C. This is number 2. From 1 and 2, we get B join C is an upper bound of the set containing elements A and C. Since A join C is the least upper bound of the set containing element A and C, since we know that least upper bound is less than equal to upper bound, implies that A join C less than equal to upper bound is B join C. number 1 proved. Next, number 2. Let A less than equal to B implies that A meet C less than equal to B. Again, A meets C less than equal to C. Therefore, A meets C is a lower bound of the set containing element B and C. Since B meets C is greatest lower bound of the set containing element B and C, we know that lower bound is less than equal to greatest lower bound. Here A meets C is a lower bound of element B and C. So lower bound A meets C and greatest lower bound of B and C is B meets C. So second is proved. Now we prove the problem number 3, in which let L with partial order relation be a lattice for any A, B, C belongs to L. The following inequalities hold. Number 1 this and number 2 this. These inequalities are called distributive inequality or semi-distributive law. Firstly, we prove number 1. Since we know that A meet B is the greatest lower bound of the set containing elements A and B, since greatest lower bound is a lower bound, so this is A meet B is a lower bound of the set containing elements A and B. So if this is lower bound, then A meet B less than equal to A and A meet B less than equal to B. This is number 1 and this is number 2. From 2, we have A meet B less than equal to B, and we know that B less than equal to B join C. Therefore, A meet B less than equal to B join C. This is number 3. From 1 and 3, here 1 and this is 3. In left side we have A meet B in both 1 and 3. A meet B less than equal to A and A meet B less than equal to B join C. Therefore, A meet B is a lower bound of the set containing elements A and B join C. This. But the greatest lower bound of the elements A and B join C is A meet B join C. We know that lower bound is less than equal to greatest lower bound. This is greatest lower bound. A meet B join C, and this is lower bound. So this lower bound is less than equal to this greatest lower bound. This is number 4. Similarly, we may show that A meet C less than equal to A meet B join C. In number 4 and 5, in right side, we see that A meet B join C. So, A meet B join C is an upper bound of A meet B and A meet C. The set containing elements A meet B and A meet C. This is upper bound, and least upper bound of the set containing elements A meet B and A meet C is A meet B join A meet C. This is least upper bound. We know that least upper bound is less than equal to upper bound. So this is least upper bound left side, and this is upper bound right side. We write this left and this right, then this will be greater than A meet B join C greater than equal to A meet B join A meet C. Proved. Number 1 proved. Now we prove number 2. Since we know that A is less than equal to A join B, this is number 1. Also, since B meet C less than equal to B implies that B meet C less than equal to A join B. This is number 2. Here we see that in 1 and 2, in right side A join B. So A join B is an upper bound of the set containing elements A and B meet C. But this is an upper bound. We have to find least upper bound. A join B meet C is least upper bound of the set containing elements A and B meet C. We know that least upper bound is less than equal to upper bound. Here least upper bound is A join B meet C, and upper bound is A join B. This is number 3. Similarly, we get A join B meet C less than equal to A join C. This is number 4. In 3 and 4, we see that in left side, A join B meet C. So A join B meet C is a lower bound of the elements, in set containing elements A join B and A join C. This is lower bound, but greatest lower bound of the set containing elements A join B and A join C is A join B meet A join C. This is the greatest lower bound of this set. We know that lower bound is less than equal to greatest lower bound. Here A join B meet C is lower bound, so we write left side, and A join B meet A join C is greatest lower bound, we write right side, and hence proved. Now we solve problem number 4. Problem is L with partial order relation be a lattice. For any A, B, C belongs to L, the following holds. A less than equal to C implies A join B meet C less than equal to A join B meet C. This inequality is called modular inequality. solution. From second semi-distributive law, we know that A join B meet C less than equal to A join B meet A join C. This is number 1. Just we have proved this in problem number 3. Since given that A less than equal to C, this implies A join C equal to C. Putting this value in right hand side of 1 here, A join C equal to C, then we get A join B meet C less than equal to A join B meet C. Proved. Now we solve problem number 5. So that idempotent law follow from the absorption law. Since we know that absorption laws are A meet A join B equal to A, this is number 1, and A join A meet B equal to A, this is number 2. These are two absorption laws. Replacing B by A meet B in 1, A join A meet B. From 2, A join A meet B equal to A. So, in place of this, we write A. So, A meet, this is A equal to A. This is the idempotent law for the operation meet. Now, replacing B by A join B in number 2. So we get here A join A meet, and in place of B, A join B equal to A. From 1, we see that A meet A join B equal to A. So here we write A. So we get A join A equal to A. This is idempotent law for operation join. Now we define principle of duality. Any statement of the lattice involving operation join and meet and relations less than equal to and greater than equal to, these are partial order relations, remains true if join is replaced by meet, meet is replaced by join, less than equal to by greater than equal to, and greater than equal to by less than equal to. Here greater than and less than equal to, we are speaking these, but these are partial order relation, means one partial order relation and reverse of it. Then lattice is L, this less than equal to, and L relation greater than equal to are called duals of each other. In problem 6, we shall show the duals. Problem 6 is show that the inequality A less than equal to C, double implication, A join B meet C less than equal to A join B meet C in lattice is self-dual. Now we solve this. The dual of the inequality, this inequality is obtained by interchanging meet and join. and replacing less than equal to by greater than equal to. Then dual of 1 is written as here A greater than equal to C, double implication. A here meet, in place of join we write meet, in place of meet we write join, here we write greater than equal to, here we write meet, here we write join, and we get number 2. Now replacing A by C and C by A in 2. Here we write in place of A C, in place of C A. In place of A we write C, in place of C we write A. In place of A we write C, in place of C we write A. And rearranging we get this is A is less than equal to C, double implication. We first write this side A join B meet C, left side. In right side we write A join B, since this is commutative. B join A means A join B. So we write A join B meet C, which is same as 1. Here we see 1. Hence the given inequality is self-dual, proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.